Hi everybody. In this video lecture, we are going to discuss about the how to calculate the lambda max values for conjugated dienes by using Woodward Fieser rules. So the purpose of Woodward Fieser rule is to calculate the position and maximum wavelength for any organic structure. So what are the rules for conjugated dienes is first we need to know the base value and we have to add up the or sum up the substituents or contributions of any organic structure so that we can able to get the total or absorption maximum. So first we need to know what is meant by base value, which is otherwise called as parent value. Suppose if the double bond lies on the same side of the single bond, it is called as cis conformation and the lambda max value will be 253 nanometer. If the double bond lies on the opposite side of the single bond, which is shown in this structure, it is called as transoid conformation and the lambda max value will be 217 nanometer. The base value may be either acyclic or homoannular or heteroannular, so many things. With the base value, we need to add we need to sum up the substituent contributions so that we can able to get the maximum absorption wavelength of an organic compound. Now look at these criteria. First one is acyclic. Acyclic, which resembles to absence of a cyclic structure. So look at this first example. There is no any ring structure, but we can able to see the 1,3 butadiene structure or conjugated dienes or alternative double bonds. So if there is no any ring, so the base value will be 270 nanometer. Look at this second example. Even though there is a ring, the two double bonds are present outside the ring. So it is also considered as acyclic. So for this example, the base value is 270 nanometer. Coming to this example, 1,3 butadiene structure 1, 2, 3, 4. There is no any ring structure. So for this also the nanometer is 217. Even though in the fourth example ring is there, one double bond is present inside the ring and another double bond is present outside the ring. So it is considered as acyclic. For the last example, even though there is a ring, both the double bonds are outside the ring, so it is considered as acyclic. So for all the example, the lambda max value or the base value is 217 nanometer. Now coming to homoannular diene. Homoannular in the sense, it is a ring structure in which the two double bonds are present in the same ring structure. Then the base value will be 253 nanometer. Now coming to this first example, there is a single ring structure and the 1,3 butadiene structure is present in the same ring. Coming to the second example, there are two ring structures but the 1,3 butadiene structure is present in the same ring. Coming to the third example, the first ring there is no any double bonds and in the second ring both the double bonds are present in the same ring. So it is considered as homoannular diene and the base value is 253 nanometer. Coming to the next criteria or rule, heteroannular diene. Heteroannular in the sense the double bond or 1,3 butadiene structure is present in different ring structure. So coming to the first example, two different rings are there and the 1,3 butadiene structure or two double bonds are present in different ring structure. Coming to the second example, the two conjugated double bonds are present in two different rings. Coming to the third example, the two double bonds are present in the two different rings. So the base value for heteroannular diene is 215 nanometer. The fourth rule is double bond extending conjugation. Apart from the 1,3 butadiene structure, that is two double bonds, if any number of double bonds is getting extended or increased, then for each double bond is getting increased, we need to add 30 nanometer. So look at this example. So the parent value here is heteroannular. So starting from here, the 1,3 butadiene is started. Here one double bonded is getting extended. So we need to add 30 nanometer to that of the base value. Coming to this example, here it is a homoannular diene. So homoannular diene means what is the base value? 253 nanometer. Apart from this, one double bond is getting extended over here. So we need to add 30 nanometer with the base value. So this is the fourth rule. Coming to the fifth rule, either ring residue or alkyl substituent. So coming to this first example, look at this first example. This is a normal 1,3 butadiene structure in an acyclic ring structure. So the base value will be 217 nanometer. So how many ring residues or alkyl substituents are there is 1, 2, 3, 4, 5 and 6, which I have marked in a red color. So for each alkyl substituent 5 nanometer must be added. Coming to the second example, 2 rings are there and the 1,3 butadiene bonds are present in different rings. So the base value is 215 nanometer because it is heteroannular diene. And the ring residues will be this one and this one. So totally 3 ring residues are there. Coming to the last rule, that is exocyclic or endocyclic double bond. Look at this first example. 2 rings are there, A and B, and it is a heteroannular diene. So for this A ring structure, there is no any double bond which is outside the ring A. But for B, there is a double bond which is present outside B, that is exocyclic double bond. So each exocyclic double bond carries 5 nanometer. Coming to the second example, 2 rings are there, A and B. The parent value for this example is 253 nanometer. But when we are considering ring A possesses 2 exocyclic double bond. So we need to add 2 into 5, 10 nanometers to that of the parent value. So these are the table we need to follow the for adding up for the dienes. Look at the first example. So this is the structure. So first we need to number the 1,3 butadiene structure. So the number starts from here 1, 2, 3 and 4. Now what is the base value is? It is a acyclic because there is no any ring structure. So obviously the base value is 217 nanometer. Coming to the ring residue, how many ring residues are there is 1, 2 and 3. So the value will be acyclic 270 nanometer and alkyl substituent 3 into 5, 15 nanometer. The lambda max will be 232 nanometer. So we'll move on to the second problem. So this is a acyclic ring structure. Even though there is a ring is there, the double bonds are present outside the ring structure. So first we need to number the butadiene structure. So 1, 2, 3 and 4. Now we need to know where the ring residues are there. So 1 and 2. So what will be the lambda max is? For acyclic it is 217 nanometer and for 2 ring residues 10 nanometer. Totally the lambda max value is 227 nanometer for this compound. Third example, this is an acyclic ring structure. So obviously we know that the lambda max value is 217 nanometer. Numbering 1, 2, 3 and 4. So what will be the ring residue is only 1. So the lambda max value will be 222 nanometer. We'll move on to the fourth example. So it is a ring structure, but the double bond is present outside the ring. So we'll start numbering the butadiene structure first. 1, 2, 3 and 4. So we can consider it as acyclic because one of the double bond is outside the ring structure. So it is 270 nanometer and the number of residues are 2. And one exocyclic double bond is there which is outside the ring. So the lambda max value will be 232 nanometer. Coming to the next example, even though it is a ring structure, both the double bonds are present outside the ring. So we'll start numbering the 1,3-butadiene structure. 1, 2, 3, 4. So it is acyclic. The lambda max base value will be 270 nanometer. Then the residue will be 2 into 5, 10. And for this particular ring, 2 different exocyclic double bonds are there. So 2 into 5, 10. So the lambda max value for this particular organic structure is 237 nanometer. Look at this example. Coming to this example, it is a homoannular diene because both the conjugated double bonds are present in the same ring. So what will be the base value? 253 nanometer. So start numbering the conjugated diene. 1, 2, 3 and 4. Next we need to denote the residues. So this is 1 and this is 2. So the total value will be 263 nanometer. Coming to the second example, the 1,3 butadiene is present in two different rings. So it is considered as heteroannular diene and the base value will be 250 nanometer. So 1, 2, 3 and 4. So what will be the ring residue is 1, 2 and 3. So we have to see whether any exocyclic double bond is there. For ring A, there is no any exocyclic double bond, but for ring B, one exocyclic double bond is there. So for that, we have to contribute 1 into 5 is equal to 5 nanometer. So the total lambda max will be 235 nanometer. Next problem, we have to number the 1,3 butadiene structure. 1, 2, 3 and 4. Then we need to write the residues. So 1, 2 and 3. So the number of residues will be 3. Now for ring B, there is a exocyclic double bond. But for ring A, there is no any exocyclic double bond. So the lambda max value will be 273 nanometer. Coming to the next problem, there are two rings A and B. Then start writing your 1, 2, 3, 4 for the butadiene structure. What will be the base value? It is a heteroannular diene. So obviously it will be 215 nanometer. Then start drawing the residues. 1, 2 and 3. 3 residues are there. So we have to check whether any exocyclic bonds are there. For ring A, one exocyclic bond is there. For ring B, there is no any exocyclic bond. So what would be the lambda max value? It is 235 nanometer. Coming to the next problem, two rings are there, A and B. We have to start numbering for the 1,3 butadiene structure. 1, 2, 3 and 4. Then we need to draw the residues 1, 2, 3 and 4. So we have to check whether any exocyclic bonds are there. For ring A, 2 exocyclic bonds are there. For ring B, there is no any exocyclic bonds. So we need to add all the substituents with the base value. So the total lambda max value for this particular compound is 283 nanometer. The next example is, it is a heteroannular diene. Start numbering 1, 2, 3 and 4. So the base value will be 215 nanometer. Now we need to write the residues 1, 2, 3 and 4. So totally 4 residues are there. So we have to check whether any exocyclic double bonds are there for these two rings. For A, there is no any exocyclic double bond, and for B also there is no any exocyclic double bond. So the total wavelength for this particular compound is 235 nanometer. We will discuss the problems for polyenes in the next video lecture. Thank you.